of special relativity, which is based on the constancy of the speed of light independent of the frame of reference. I will show how length and time is measured differently for different observers by deriving the Lorentz transformation laws using simple symmetry arguments. And I will, as a result, show the consequences of this theory, such as length contraction and time dilation. So let's start. Suppose you have an observer here, and you have another observer here, and one of the observers is moving with the speed of v with respect to the other. Suppose the observer A is stationary and observer B is moving with a velocity of v with respect to the other. And what we would like to find out is how the length and time measured by the observer A is related to the time and length measured by the observer B. And we're going to use the following argument: the speed of light, which is c, is constant for all observers. And this is the central assumption in theory of special relativity. And we are going to make use of this. And we're going to take the units in such a way that the speed of light c is 1 to just simplify things. So if my time is, for example, 1 second, the units for the length is going to be light seconds. So the unit will be the length units will be the amount of length that the light will travel within 1 second is going to be the length units. So once you fix the speed of light at 1, you only need to choose the unit of the length or just the unit of the time. If you choose one, the other is chosen already. And what we're going to do is now, the first thing we're going to do is we're going to assume that any change in length, suppose there's 2 processes. Two events separated by a distance of delta x and a time difference of delta t. And these 2 events are seen by the observer A as separated by delta t and delta x, but the observer B sees these events, like say it has some machine that it observes these 2 events. It's going to see the 2 events happening as if there's a distance difference of delta x prime and time difference of delta t prime. And let's assume that there is a transformation, that a matrix transformation that will make this calculation possible. Suppose that the transformation from delta t delta x to delta t prime delta x prime is a linear transformation, and suppose that there's a matrix TV that will do the job, and our purpose is to find out what that matrix is. And we're going to see that this is the Lorentz transformation matrix, and we will find it in terms of the value of the V. So that's our purpose. Let's see what kind of matrix will do the job when transforming the time and the length from delta t delta x to delta t prime to delta t x prime. Okay, And we're going to use very basic arguments. We're going to use some clues to be able to do that. Very simple symmetry arguments we're going to use. Okay. And the first thing that we're going to use, as we said, is the constancy of the speed of light. What we mean by that is that suppose this event that's separated by delta t and delta x is light moving from one place to the other. Suppose there's a light source here, and then the light is traveling from here to here. And within a time of delta t, the delta x traveled by that light will be c times delta t. Since we take c to be equal to 1, delta x will be equal to delta t. Okay, this is based on the observer A. And but what about the observer B? What is the observer B seeing here? The observer B will see exactly the same speed of light, meaning that the delta x prime and the delta t prime, although it's not necessarily going to be equal to the delta x and delta t, the ratio between the two will be the speed of light again, because it's going to see the light the same way as the observer A is seeing. So this is going to be c, which is equal to 1. So meaning that delta x prime equals to delta t prime. So we actually obtained one clue about what this TV must be. This linear transformation must be in such a way that it's going to turn the delta t into delta t prime, delta t prime. Okay, so what it does is the first clue tells us TV turns delta t into delta t prime, delta t prime. Okay. And you can think of it as, this is some multiple of 1, 1 vector, and this is some multiple of 1, 1 vector. So it looks like the TV has an eigenvector, and that eigenvector is 1, 1 because of this equation. And say it's going to have an eigenvalue of lambda plus. Okay. And this is the first, clue. So we found that one of the eigenvectors of TV is 1, 1. With similar arguments, we can assume light traveling from here to here towards the negative x direction. And in this case, our delta x will be negative delta t, because now I'm taking the displacement to be negative. Delta x will be negative delta t. And with the same arguments, we're going to find out that TV delta t minus delta t will turn into delta t prime minus delta t prime. So this will tell us that another eigenvector of TV is going to be 1 minus 1. And it's going to turn it into lambda minus 1, negative 1. So we found that the very simple argument that the speed of light is the same for the two observers, we found that this transformation matrix, which is the Lorentz transformation, has two eigenvectors, and these two eigenvectors are 1, 1 and 1 minus 1. Now, using these, we can write a very general matrix, A, B, D, and E. I'm not using the value C just not to confuse it with the speed of light. But say we have 4 entries, and we want to find out the values of A, B, D, and E in terms of the velocity B. And one clue we obtained is actually 2 eigenvectors. So I'm going to make use of it, and I'm going to say A, B, D, E, if I operated on 1, 1, I will get some lambda plus 1, 1. That's my first equation. And then my second equation is AB, DE, 1 minus 1 is lambda minus 1 minus. Right now, I'm saying nothing about how lambda plus is related to lambda minus. So let's just take them as two different eigenvalues, not necessarily equal eigenvalues. Okay, the first equation tells us that A plus B equals to lambda plus and D plus E equals to lambda plus. I'm just doing matrix multiplication and I'm actually equating the matrices vectors element-wise. And the second matrix equation gives me A minus B equals to lambda minus and D minus E equals to negative lambda minus. From these equations, I get A to be equal to lambda plus lambda minus over 2. And I find B to be lambda plus minus lambda minus divided by 2. And then from here, from these two equations, I find D equals to lambda plus minus lambda minus divided by 2. So these two are same. So B and D are same. And then we found E equals to lambda plus lambda minus divided by 2. So these two must be equal. So A is equal to E and B is equal to D. So A equals to E and B equals to D. So our matrix, the transformation matrix, will take the form AA and BB. Okay, so this is one clue. Now we need to get more clues about this system. So how does this TV behave? Okay, the second clue we're gonna get is by introducing so-called the parity operator. Let us introduce the parity operator. And with the parity operator, I mean switching the positive distances to negative distances. So it's like taking the mirror image of the coordinate system. So in your coordinate system, if you have the plus x towards the right direction, minus x towards the left direction, you flip it and you turn the minus x to the right and positive x to the left. Okay, so this is the parity operator. So this is like suppose you have a ruler, 0, 1 inch, 2 inches, and so on. What you do basically is you rotate this like that, flip it, and then your ruler shows like 0, 1, 2, etc. So the parity operator is taking the mirror image of your object and your coordinate system. Okay. And then we're going to suppose that the behavior of TV does not change with the parity operator. I'm going to write it in a more clear way. But the idea here is that the space along the x direction is symmetric. If I flip the coordinate system, I should get the same physics, same results. So that's the idea. Okay. Now, again, let's put our observers, observer A, and then here observer B, and this observer B is in a bus or in an aircraft or in a space shuttle, and then is moving with a velocity v. And still, I'm assuming only one dimension in space. but these things can be applied very easily to more than one dimensions. Once we get this idea working nicely for one dimension, it's very easy to apply it for more dimensions. So here's what we're gonna do. Suppose this observer A is measuring some distance with the ruler. And suppose we apply the parity operator to the object under interest that the observer A has. So using the parity operator means you flip the direction, and then once you flip the direction, once your object becomes the other way around, like let's make a direction like this. Okay. This time, and your coordinate system, the coordinate system of A, like plus, minus, using the parity operator, you turn it into minus, plus. And then when you do this, when you apply this parity operator, now the velocity of the object or the velocity of the observer B is reversed, because now the coordinate system of A is reversed. So the velocity of B is not now plus V, but it's minus V. So any Lorentz transformation I will do after applying this parity operation will be the Lorentz transformation representing the velocity minus V, not the velocity V. Okay. And then I move on to the coordinate system of observer B. Now I flip the coordinate system again. I use another parity operator. Okay. And by applying these two parity operators, one in the coordinate frame of observer A and then the coordinate frame of observer B, I obtain a normal Lorentz transformation as if the object is originally moving with a velocity v. The reason is because I applied the parity operator twice. Now the coordinate system turned back to its original direction. Okay, now I have the plus is along the right and minus is along the left. Okay, but here the important part here is that when you apply the first parity operator, the second transformation TV is based on the velocity negative v, so that's why we apply the Lorentz transformation for the velocity v. Okay. Now, also note that t minus v is the inverse operator tv minus 1. The reason for this is because the observer B, so like if you do two operations, like one operation and then another operation along the other direction, say you have one A and then B here. If you do one transformation from here to here, and then another transformation from here to here, t minus v, that will cancel out. So you go back to the original state. So there is going to be no change in the delta x, no change in the delta t's. So it would be as if, you're applying a unit matrix. So t minus v is the inverse of tv, we can say. Now, noting this, and also the inverse of the parity is also parity itself. So let me apply p on both sides this equation. If I apply p on both sides of this equation, I get unit matrix, and then I get t minus bp equals to ptv. And then if I apply the tv to both sides, what I get is, since these are inverses to each other, this is 1. So I get parity is equal to TV, P, TV. Okay, so we're going to make use of this equation to get one more equation about the elements of the TV. Okay, and the parity operator is, note that the parity operator is 1 minus 1, 0, 0. The reason for this is the parity operator does nothing but converts delta t delta x into delta t minus delta x. So it's doing nothing to the delta t, but it's flipping the delta x. Okay, so with this, the matrix that will do this is nothing but this one. It's only changing the direction of the delta x. So this is P. And then this is equal to TV, which is AA, BB, and then the parity 1, 0, 0, minus 1, and then A, B, B, A. Okay. And you can actually take, like factor out A here, A, 1, B over A, B over A, 1, and then 1, 0, 0, minus 1, 1, E over A, E over A, A. I factored out another A, so I have A squared here. Okay. Let me do this part first. So let's see what I can get. A squared, 1 times 1 is 1, B over A times 0 is 0, so you get 1 here, and then you get minus B over A here, and then you get B over A here, and then you get minus 1 here. Okay, times 1 B over A, B over A, A, and then we get A squared, and also let's simplify. Let B over A be equal to, let's say, some number S. Okay, so we have 1 minus S squared, and then we get, no, so this is 1, sorry. This is 1, so we get 0 here, 0 here, S squared minus 1. And since this is equal to the parity operator, 1, 1, minus 1, 0, 0, we see that A squared 1 minus S squared becomes equal to 1. From here, A is nothing but 1 over square root of 1 minus S squared. So our matrix, Lorentz transformation matrix, looks like TV equals to 1 over square root of 1 minus S squared, 1, 1. Here I have S, S. Yet S to be found. So we need to find out the value of the S. Okay. So what else can we do? Now, one more trick. The third thing we're going to use. So far, we have used the constancy of the speed of light and the parity argument. Now, the third thing we're going to use is the transformation of a very simple case, which is, suppose the observer A has an object here which is not moving anywhere, which is stationary with respect to the observer A. So the delta x is equal to 0 for this case, but the delta t is non-zero. So the time is ticking by, but the object is at the same location. So let's see how the observer B sees this. It goes with the velocity v, and then say the delta x is delta x prime now, and the delta t is delta t prime. But here's the idea. The observer B will see observer A as moving to the left with a velocity v, with a velocity minus v. So it will also see this object moving to the left with a velocity v to the left. So basically, this delta x prime divided by delta t prime must be equal to the velocity of this object that observer A sees as stationary, which is negative v, because from the observer B point of view, it's the observer A moving to the left with a velocity v, and also this object moving to the left with a velocity of v. So the delta x prime divided by delta t prime must be equal to negative v, because the velocity of that object must be seen as negative v by observer B. With this clue, what we can do is the TV applied onto delta t, which is non-zero, but delta x being 0, must be equal to, now, some delta t prime and negative b times delta t prime, because delta x prime is equal to minus v times delta t prime. Okay. With this, what we can do is we can write down what we have found for TVs so far. So I'm going to place this one in this equation. 1 over square root of 1 minus s squared. 1 ss. And then we find, delta t 0. And this must be equal to 1 minus v times delta t prime. Okay. Now let's see. If you do the left-hand side, we get 1 over square root of 1 minus s squared delta t, and then s delta t equals to delta t prime negative v delta t prime. Okay. So the ratio of these two must be the ratio of these two, and then you get simply s is nothing but the negative v. Okay. With this, the TV can be written simply as 1 over square root of 1 minus b squared, 1 b, minus b minus b. So this is the transformation law, Lorentz transformation law for one-dimensional space. And then you can obtain the Lorentz contraction, length contraction, and the time dilation by using this. Say, for example, you have an object which has a length of delta x, and it's stationary in the point of view of observer A. And then what's going to happen is the delta x, delta t will turn into after multiplication, we get delta x minus v delta t. Yep. And negative v delta x plus delta t. Okay, so this tells you what the delta x prime is. The delta x prime is 1 over square root of 1 minus v squared delta x minus v over square root of 1 minus v squared delta t. And the delta t prime is 1 over square root of, minus v over square root of 1 minus v squared delta x plus 1 over square root of 1 minus v squared delta t. Okay. But this is not immediately showing what is the Lorentz contraction, like how much length change will the objects experience from moving from one reference state to the reference observer to the other reference observer. In order to understand this, we need to think about what is a length measured by observer B. So basically, a length observed by an observer B is simply the delta x corresponding to no change in time. So when we measure, for example, things with our rulers, we measure it specifically at the same time for our time interval. So basically, if it's the observer B measuring this, observer B should make sure this delta t prime is 0. So it's only when delta t prime is 0, then the observer B will measure the distances correctly. So if delta t prime is 0, then what we get is negative v delta x over square root of 1 minus v squared plus delta t over square root of 1 minus v squared is 0. From here, we get delta x v delta x equals to delta t. And then to use this one and plug this in to this equation, delta x prime turns out to be 1 over square root of 1 minus v squared delta x minus v times delta t, which is v squared times delta x. And from here we find 1 minus v squared divided by square root of 1 minus v squared delta x. So we find that delta x prime is simply square root of 1 minus v squared delta x. So we see that the observer B sees the object at a length delta x prime instead of delta x. So this delta x prime is smaller than delta x if v is smaller than 1, which is the speed of light. Okay, so this is the Lorentz contraction. So this is all for today. Thank you for watching me. Have a great day.